Hello everyone. In this video we're going to cover how to use the mineral inversion module. Mineral inversion may be a new topic to many non-petrophysicists, as there are no commercially available G&G packages outside of Danomics that have an option for performing mineral inversions. This means that mineral inversions have typically been limited to the realm of the petrophysical specialists who are using specialist packages such as TechLog or Interactive Petrophysics. You may be wondering, what exactly is a mineral inversion? A mineral inversion is a method of solving for the mineral and fluid constituents of a rock. You may be answering, for example, what are the volumes of clay, quartz, calcite, dolomite, water, and oil in a rock? The value of this type of calculation is twofold. First, having the mineral volumes can help you evaluate properties such as the lithophases or the brittleness of a zone. Second, and more importantly, is that it provides you with a way to calculate a grain density, which can then be used in the porosity calculations. And this is specific to each depth step. This gives you a far superior answer to traditional methods like a density porosity, where a constant matrix density is used throughout a zone. So let's get started. So here we are in the mineral inversion. So if you're not on this module, to get to it, just go to the module selection menu and select Inversion. And this is what you'll see come up by default. So you will see a series of parameters that correspond to different minerals, and then a list of curve names. And then over here you'll see a track that shows the mineralogy, grain density, the porosity that's being calculated from our inversion, as well as the actual and predicted curves from this well. So this module is a little bit different than the other modules in Danomics in terms of its appearance, and this is because we're working with a matrix of data. So when we're doing this, what we're going to do is we're going to start off with setting a default, and that default will be applied to all zones, and then we can go through and we can customize each of these zones. So when you're doing the mineral inversion, it's considered good practice to only use the constituents that you expect to have in your system. So, for example, here in the Alston chalk, we don't really expect to have much dolomite or pyrite. And also this is a gas area, so we're gonna set up our gas, and then, however, in some intervals, such as the Eagleford, this is an organic shell, and in this interval, we will expect to have some pyrite. So the way we go about setting that is, now that we've set our defaults for all the zones, we can come here to this drop-down menu, we can select the Eagleford shell, and we can turn pyrite on for this specific zone. So once we've done that, we can now see that pyrite has been calculated in certain portions of the interval. As I've made some changes, we may want to reset our colors here. So I'm going to turn gas to a bright red color. And I'm going to set my kerogen to be black in color. And so now we can see our kerogen calculated here in the Eagleford, and we can see gas being calculated throughout this portion of the interval. And there are some more modifications we'll make along the way. But this is how we set up our general inversion. In terms of the curves that are being used, we have density, neutron, our U curve, which is a product of the density and the PE curve, sonic, conductivity, our V clay and our V kerogen curves, which come from our early interpretations, and unity. And unity is quite simply making sure that our volumes sum to 1. Then we also have an option here for mode. Mode is how we want to try to fit the curve. There are 3 options we have here: fit, constraint, and disabled. So constraint says that it will force the solution to give an exact match for that curve. Fit is that we will try to fit that curve within the confidence interval. So we're going to use the confidence interval as a weighting parameter for each curve. and disabled means it will not be used in the inversion. So when we evaluate our results, the way we evaluate this is we want to look to see what is the variation between our predicted curve and our actual curve. And so here, if I zoom in, you can see that we have a bit of variance in between our predicted value of sonic and our actual sonic value. So let's start by evaluating this property. So in general, with our mineral constituents, most of these properties are quite well established and have very little variance. So for example, quartz has a sonic value of 56, calcite 49, dolomite 44, for example. And these have been measured extensively and there's very little variance. However, as we're using a generic clay, and as you'll know, the sonic value will vary with compaction. You know, there is quite a bit of leeway in the value for clay. Also, depending on the fluid compositions of our water and gas, we can also see some variation there. So let's start off by trying to tune our sonic for the clay. So we're going to set up a cross plot here, and we're going to select our sonic clay cross plot, and we're going to look at this from all formations. And what we see is that we have our sonic value topping out at around 100 when we're at 50% V clay, and we see that our sonic rarely gets above that. So 120 may be a bit too high of a value. So we can come in here, and we're setting this for the default zone, and that sets our clay volume at 100 for the sonic. And now we can see that we get a much better fit through this interval. Okay, so that is that's how we can tune a parameter. You know, this well doesn't have a PE curve, but if we had a PE curve, we could set the PE for clay in a very similar manner. Now, one thing to notice here is we are predicting a conductivity, and our predicted conductivity is we're not getting a very good match relative to our actual conductivity. Part of the reason for this is that we have it disabled by default. But if we come on here and we turn this into a fit, and now, you know, it recalculates the solution, and now we see that we get a much better fit for our conductivity relative to our measured conductivity. And so there are some tuning parameters here for our clay. And so it's important to note, one of the things that we're doing is we're using conductivity instead of resistivity. And all conductivity is, it's the reciprocal of resistivity, typically times 1,000. And so as you're, you may be wondering, well, we normally use resistivity, why are we looking at conductivity here? And the reason we're looking at conductivity is because most of your minerals, such as quartz and calcite, have zero conductivity. Zero conductivity would then mean infinite resistivity, which would be quite difficult for us to model. So that's why we're using conductivity. Okay, so you know, with respect to our conductive minerals, you know, really we have pyrite, clay, and water that are conductive. And so, you know, we can tune those in a very similar way. So if we look at a clay resistivity cross plot here for all formations, we can see that our clay resistivity, as we're coming out to our highest V clay values, is somewhere between 3 and 4 ohms. So if we remember that the clay is that the conductivity is a reciprocal of the resistivity, we can simply do that calculation and say that 3 ohms is roughly equal to a value of about 333 for our clay. So we'll set that. This will allow us to further tune our conductivity. And then we also need to consider the conductivity of our water here. And this is something that you may wish to get your water resistivity from a lab analysis. But for this area, I happen to know that our conductivity is around 8,000. And so we're going to put that value in, and now we've updated that for all the zones. And if we want to force a bit of a tighter constraint, we can simply tighten up our confidence interval. So let's put that at 250 instead of 500. And now we see we get a much better fit here on the conductivity. So that is how we go about doing our mineral inversion. And once again, you can tune this on a zone by zone basis, and you'll notice that all the values that I typed in here to my default are also now present in each of my zones. So those changes do propagate through each of your analyses. And so now to utilize the output from our mineral inversion, there's only one step that we need to take, which is we go to the porosity interpretation, and we simply select that we want to use the mineral solver porosity. You'll notice there are two options for our mineral solver porosity. There's mineral solver porosity and mineral solver porosity strict. The strict method takes the exact total porosity that comes out of the mineral inversion, whereas the mineral solver porosity will still allow you to set your fluid density separately. So it's really up to you which one you want to use, but moving forward we're going to use our mineral solver porosity in strict mode. So we're going to jump back to our inversion module, and we're going to inspect our results one more time, but in general it looks like we're getting an excellent solution here that matches the lithology that we expect. So predominantly siliciclastics up here in our upper interval, very high volumes of calcite in our Alston chalk. Our Eagleford is a very calcite-rich clay, so that makes sense. And then once again, the Buddha is a tight carbonate interval. So it looks like our mineral inversion is giving us the results that we expect. Okay, I hope you enjoyed this video, and as always, remember to save your work before you move along.